the column, the resolution potential of the column is by increasing the number of theoretical plates, and the way we achieve increasing the number of theoretical plates is to have a smaller bead size, right, on there, because the plate height, which is what we're trying to achieve by minimizing that plate height, is this arbitrary, not arbitrary, but this theoretical construct. It really refers to how much of the surface of the stationary phase do we have to interact with analytes in the mobile phase. Okay. And that's what that's saying here. So if we now have this goal, say in the real world, we have a goal to maximize the resolution and performance of this chromatographic method. And what things do I have in my control that I can change or optimize in order to achieve that? And one of them is to minimize theoretical plate height, right? To make it smaller, which is going to provide more separation, more partitioning surface area upon which my analytes can partition, and ideally then lead to greater separation potential or resolution potential. That makes sense? And you don't look convinced. All right. So if you were to go to the Dynex website, you see, or the Waters website, for all these manufacturers, for many of the columns that they sell those columns with different particle size or different bead sizes, right? That may vary, right? And of course, their goal is to try to, it's not just about having smaller beads per se, because sometimes there's things that come, there's sometimes downsides of things that come with smaller beads, and that is it becomes much harder to actually push fluid through the column as they get packed with smaller bead sizes, because there's less space around the beads because they're packed more tightly, right? And these beads are typically in the 10 to 50 micron diameter range. So they're really tiny, right? They're like much tinier than a fly speck or something like that. So they're really tiny, and they pack a whole bunch of them in. And the downside of getting too small is the hydrodynamic characteristics of the column change, become poorly manageable, right? So there's a trade-off. So what about that does not make sense?
When you connect that with a height plate, and it just
Right. So this is theoretical. This construct. Right? This is reality. And we use this theoretical construct with plate height in order to sort of build equations that we can utilize to predict and explain how analytes actually chromatograph or elute across a column, and how we're able to separate them. How we achieve this is actually through the physical properties of what the column is composed of, the packing of the column. And there's the functionalization of the solid material. There's what the solid material is made out of, right? Okay, and how big it is, and its dimensions and so forth. And so the comparison of the reality with the theoretical construct is that we would say that each of these plates that don't really exist really is describing the process of partitioning onto the surface of the stationary phase. Right? And the only difference now is that here we're ascribing some theoretical physical dimension to this, when in reality it exists like this. It doesn't actually have that kind of physical dimension. But the physical-chemical properties of how analytes are partitioning, it can be onto the solid stationary phase, can be explained with the plate theory in terms of considering these theoretical plates. So if we back up and say, all right, this is theoretical, this is reality, and I know that my goal as an analyst is to optimize, but optimize separation of analytes, right? And in the shortest amount of time, and I have several things under my control in order to achieve that. And one of those is to increase the number of theoretical plates in my column, which is the surface by which things can partition. And the only way I can achieve that is by decreasing the plate height. And the only way I can achieve that is by having smaller beads where I have a larger surface area to volume ratio, where I have a greater amount of exposed stationary phase surface area in my column. Right? And so what do I do to do that? I don't do anything physically other than get on the computer and I buy a different column that has a different bead size to achieve that. Right? I would do a chromatograph. I would get some kind of a chromatogram from that elution. I would look at some of the parameters I have control over, and one of the decisions I might consider making is whether to try a different column, possibly that has a smaller bead size, if I'm not adequately resolving some peaks. So I have control over that. So to optimize resolution, that's one thing I can do. Okay, and I can decrease the theoretical plate height by applying a column some more. Okay. The two other things that I can try to optimize relate to the retention, or it's also referred to sometimes as the capacity factor, retention factor, or capacity factor of the column, or the selectivity factor. And we've talked about these to a small extent. Okay? The retention or the capacity factor is simply just the ratio of the retention time versus the mobile phase elution time, right? And so if you look at a chromatogram, we know this is the mobile phase elution time, right? So this is Tm to there, and for this one, that is Tr to there, right? You draw that. And then the Ts, the elution time of my sample is the difference between the retention time, starting from 0, and the mobile phase elution time. Okay. And so I can calculate what the retention or capacity factor is, knowing those things. I can calculate the selectivity factor of my column of knowing the sample elution time, which is this, okay, for several different peaks, peak B versus peak A, right? And that just tells me how close or far apart those peaks are to be. So how do I optimize these parameters? You optimize these parameters by modifying, optimizing the properties of mobile phase. That's what it basically comes down to. Is you have control over which column you use, the properties of the column, and the composition of your mobile phase. Changing things like mobile phase flow rate and things like that have a small effect on resolution. They may have effect on peak broadening and all those things that you're discovering with the Van Dieter, hopefully, but they have a very small effect on resolution. So change in how fast you're pumping the mobile phase through the column isn't going to buy you anything other than having things move out more quickly. It's not going to change the resolution. The only way you can modify that to optimize it is by modifying a composition chemistry of the mobile phase or properties of the column. So if I were to ask you, if I were to give you on a test, say, here's a chromatogram, and clearly you can see that there's poor resolution of two peaks here. And I might say, what do you do? And you wouldn't say, oh, well, I'll just slow down the mobile phase flow rate, and I'll just separate. Because of course that won't happen, right? You'll just get a broader double peak. And so you'd say, well, I would first maybe try to reduce my plate height, and by reducing the particle size in the column to increase the surface area upon which the analytes are partitioning. I might change the properties of my mobile phase, what kind of column this is, change the properties of the mobile phase, and I might try to see if I can separate these by maybe changing the pH or changing the ionic strength or the organic composition if it has a non-polar or polar organic solvent in it. I do something that I would play with empirically to see if I can change and optimize that separation. Have a sense of that.
So you're saying a smaller bead size is going to be more resolution. So is there going to be any time when you want a larger bead size? Or why wouldn't you just always want to have like the smallest size possible?
Because
Besides the price.
Well, so there's a price component, and with the smaller bead sizes, they're limited by flow rate, and they have a more limited flow rate potential, so you can't pump mobile phase through as quickly because the pressure builds too high because of the resistance to flow through. And so there's a trade-off of you pay more, and typically your flow rates are lower. So if the flow rate's lower, the elution time is longer in general. So there's a trade-off of it takes me an hour to chromograph instead of 40 minutes or 30 minutes or whatever. So those are just some of the factors that come in.
Are beads the best geometric shape to use for the highest surface area to volume ratio? Wouldn't discs be better?
Or would what be better?
Discs.
If they were like packed in there a certain way?
Yeah, I guess, yeah.
I think, yeah, you might say there's probably shapes that would maximize the surface area to volume ratio. And then I think the reason they typically use spherical beads is because they can literally pack them in a column. And it's not a matter of just packing more surface area, because you could have sort of like something that's, you could have infinitely small bead size, or like you're saying, a disc that has a much higher surface area to volume ratio. But if they pack incorrectly, then they either provide too much space in there, you can't pack as many because of how they arrange themselves, or maybe they pack so tightly that wouldn't be space for a fluid to go.
Well, couldn't you just like functionalize both the sides of the column and the discs themselves, and they would just repel each other?
See, you have a future working for these ideas. I don't know. That's a good, I think that there are people who literally whose careers they spend doing those things. Yeah. And so why we have the available columns that we have and not other ones probably reflects that they find of ideas, try them, and some work, some don't. But I think that's the field of chromatography is all about doing things like that and trying them and seeing how effectively they actually work. And it's actually a pretty big business. Okay. So, I talked a little bit last time about different elution strategies, and the difference between an isocratic elution, which is where the composition of the mobile phase does not change over the course of the elution, versus a gradient elution, where the composition of the mobile phase does change over time, where you have maybe a mobile phase that was water with a acetate buffer, and one that was either acetonitrile or methanol or some sort of polar solvent. And over time, you would gradually be mixing the percent of one mobile phase would become less, and the percent of the other mobile phase would become more. So that by the time you reach the end of your elution time, the mobile phase is 100% of the other buffer and none of the first buffer, right? So you had buffer A and B, and the percent of A would decrease, the percent of B would increase over time. And what that does is, by changing the composition of the mobile phase in a linear fashion, which you can program it over the elution, is that you can then more effectively select for the elution of different analytes that have quite different chemical characters. So you're doing the isocratic, but you're not modifying that. But most reverse phase, HPLC kinds of applications, chromatography, the majority of those use a gradient elution profile. These two different buffer systems, phase systems. And in both cases, you can actually determine the resolution of samples by knowing some of the things we just talked about, by knowing the theoretical plate height, or the number of theoretical plates, which is going to be determined by the plate height, by knowing the selectivity factor, by knowing the retention capacity factor. You can use those parameters that are all determined by the chromatogram and the calculation of knowing your plate height, your column length, to actually calculate resolution and maximize resolution. And so, rather than use an empirical approach just based on how the peaks look, one could actually calculate under certain conditions what the resolution is. And this is what manufacturers would do, or what people would do in reporting. They're developing a chromatographic method. In reporting in their papers, they would actually calculate for that method what the resolution was. And this would allow people to compare, if they're trying to get same analytes using different methods, is to compare the performance of different methods for separating those analytes from one method to another. Rather than just say this chromatogram looks like this compared to that, they can actually quantify what the resolution was of that method.
So this resolution is specific to the method for analytes tested in that method?
Yes.
Okay.
Exactly. That's right. And so for you, you'd say, for the separation of these anions in my unknown samples with my method, I can calculate a resolution for each of those peaks, for each of those anions. And somebody else come on and say, oh, I have a new and improved anion exchange column, and I think it's going to actually provide greater separation for some peaks. And they would go ahead and then have their method of their mobile phase, and they can calculate the resolution for each of the anions in that method. And compare and say, which will provide better resolution to that.
Is resolution measured in any kind of units, or is it just the number?
What are the units here? That's a good question.
Like, if we calculate that and put it in a report, are we gonna get like, are we gonna have to include
Well,
like
we know,
number of somethings for whatever?
We know that this has a length dimension. This has a number dimension, but it's based off the length of the height of the plates, right? So this is a number, right? Just
Yeah.
a unitless number. This is based off of
That's a ratio.
essentially time, right? But it's a ratio of the same, so that cancels out, so that becomes unitless. So I think it's unitless. I think it's unitless. It is unitless. Let's go through it. Okay.
I want to talk a few minutes about detectors beyond what you've experienced for yours, for the chromatograph that you're using in class. Because I made a point of saying before that for liquid chromatography, that HPLC chromatography is probably by far the most commonly used. And in all chromatographic systems, the point, like you said earlier, is to separate analytes the sample, right? And of course, we have to be able to detect what those analytes are, but in the vast majority of cases, in chromatographic systems, the detectors are just what we would characterize as bulk detectors, just like in yours. So in yours, your detector is measuring what in your system?
The ion.
Okay, so it's measuring, this is actually kind of a trick question maybe.
Resistivity.
So what is it actually
Impedance.
Resistance?
Impedance.
Note to self, put this quiz. So what is the detector? What kind of detector is your detector?
Measures the inverse of conductance of AC current. Okay. I forget what it's called, but
So, okay,
it's for AC, not for
that's true. So you have a conductivity detector, right? And if it's a conductivity detector, I would infer that it's measuring conductance, right? And I did make the point of saying that conductance is determined by, in an alternating current circuit, determined by impedance. Right? But what you're actually measuring is conductance. Right? So your signal in, what is it, micro?
Siemens.
Is it micro? I can't remember what the micro or whatever. Okay, is a measure of conductance, right? Okay. So so the conductivity detector is a bulk detector because it's not telling you who's conducting. It's just telling you that there's things in there that are conducting. The higher the anion content, whatever those anions are, the greater the conductance, right? And so we rely on the fact that we've separated those anions with the column to actually determine who they are based on the retention times. But the detector doesn't help us with that. It only helps us with how much conductance there is. And so in most liquid chromatography systems, they are equipped with similar kinds of bulk detectors that measure some bulk property of the analytes that are flowing through the detector cell. And that could be refractive index, which is relatively uncommon. In most cases with HPLC or other kinds of liquid chromatography methods used in the biomedical industry, detection is based on UV visible absorbance, right? Just like you just did, right, with lab 1. And that UV vis, of course, can come if it's a really inexpensive detector, it's a fixed wavelength where I can only measure at this wavelength, right? And oftentimes it's very effective, like at 230 or 280 nanometers or something, where the peptide bond or aromatic rings on amino acids may strongly absorb. And people use it as a way to detect concentrations of proteins or aromatic, proteins based on aromatic amino acid content or peptide bond content or DNA, measured amounts of DNA, because all those biological molecules absorb pretty well at the 215 to 230 to 280 nanometer range of the spectrum. So they're fitted with detectors that are relatively inexpensive that can do that. The next grade that I'll talk quickly about is what's referred to as a variable wavelength one, which is just like what you guys had. You use a variable wavelength UV vis spectrometer, right?
and you had a source of ultramagnetic radiation that was what? What was your source of light?
Deuterium.
The deuterium arc lamp, D2 lamp, right? And that deuterium arc lamp generated a broad wavelength band ultraviolet light, electromagnetic radiation that spanned across a whole range of wavelengths, right? And you use the monochromator to select the wavelength you want based on the absorption maximum of your complex, right? Well, the same concept is used in liquid chromatography, that they can have these variable wavelength detectors, and for a variable wavelength detector to work in liquid chromatography, it has to be just like it was in your UV spec. There has to be a source of broadband light, and there has to be a way to select certain wavelengths from that, and it works very similarly. Both in UV-Vis instruments and in HPLC detectors, probably a more commonly used kind of detector method now is what's called a diode array. And the diode array allows essentially a simultaneous measurement of many different wavelengths, not just one at a time. Fluorescence detection is common. We talked about conductivity issue. Probably some of the most, I think, powerful kinds of methodologies that utilize liquid chromatography is when the instrument is married up onto some other kind of detector system, like mass spectrometer. And so we've done a lot of methods where we developed methods because we were interested in understanding the speciation of arsenic in human urine samples. And so if people get exposed to arsenic, groundwater or whatever, they metabolize that. Some of it remains as inorganic arsenic. And it goes from arsenic 5 in the environment typically, gets reduced to arsenic 3 in your body, then it gets converted into different organic forms of methyl arsenic, monomethyl, dimethyl arsenic, other different kinds of organic species of arsenic. And each of those kinds of species tells us something about the potential effect of arsenic in the person. And so we would collect, we got urine samples, and we would separate the arsenic species in those urine samples, called chromatography method, liquid chromatography, and have the eluent come out of the column, like a your column, go right into a mass spectrometer, where we can then look at the different arsenic species by mass spectrometry. So we can identify the different arsenic species that came out that we detect by mass spectrometry, but separate by liquid chromatography. And so there's lots of those methods. They commonly refer to them as sort of hybrid methods because they're varying liquid chromatography mass spec. In the chemistry department, there's several different LC mass specs that separate samples into peptides and fragments of biomolecules and then analyze them with a different kind of mass spec, not an element of one, but a mass spectrometer. So there's a lot of different kinds of methodologies. It's almost limitless of people have developed looking at that. So I want to, step back a second and say now, with all detectors, because detectors then have some potential, electrical potential applied, and then when something hits the detector, whether it's a photon, typically, or depends what or if it's an ionized atom, it's a different detector. When that thing that we're trying to detect hits the detector, it generates some type of response. Typically, the kicking off of electrons that would generate a cascade and ultimately a potential we didn't measure. We'll talk much more about that. It's the detector that is essentially the source of the noise. The instrument is incurring into our measurement, right? And so we went in with the UV-Vis spectrometry experiment where you measured blanks 3 times and saw what that absorbance was 3 times. And if that absorbance was varying from, between when you hit read a bunch of times, if that absorbance was varying just a small amount, it was varying due to electronic noise coming from the detector of the instrument. Okay? And so if you were to blow up sort of what that noise might look like in terms of a baseline, or in real time, so this is over time here, you'd see, you could blow it up enough that there is this electronic noise that is generated at the point of the detector that in some cases may limit our ability to distinguish what is a real response versus what is just noise at the background noise. And that's what we are using, what you're using to determine the detection of your instrument, right? How noisy is the instrument detection compared to the measurement of the true analog signal. So for your experiment right now, your lab right now, you're faced with two options. You've already faced this. And one is, I'm going to analyze some blanks a bunch of times, at 20 minutes or 15 minutes each, to try to determine what my detection limit is, based on how reproducible those blanks are. Or, if I don't have the time, the luxury to do that, because we have some other things to analyze, I can try to evaluate what my baseline noise is, and use a simple approach that my detection limit can be estimated by looking at a ratio, or assuming a ratio of 3 to 1 for my signal to noise ratio. So I can characterize what my baseline noise is, signal is, and multiply that by 3, and then estimate a limit of detection using a 3 to 1 signal to noise multiplier. Have you guys done this yet? Okay, so you need to do it, right? So you say, how do I do this? Well, you would say, here's my chromatogram. I get chloride and this and that, and all these things come out. And now I want to know what my baseline noise is. And so what you have to do is you have to say, well, if my peak is eluting up over a time frame like this is time, of course. If my peak is eluting up time period, I want to know how noisy is my baseline over that similar kind of a time area, right? Now I know that depending on the size of the peak, the time it takes to elute varies a little bit, but you could, in your chromatogram, go and say, I'm going to, in a place where I think it's a baseline, like maybe here, and maybe here and here, where it's a similar time interval over which my peaks might be eluting. And I can now take this and blow up my axis here to see this, and now I can integrate the signal over this area, right? So right now I have peak 1, peak 2, peak 3, peak 4, peak 5 that the software has identified. And I need to go back in and define to say, I want to measure the peak area over this time area, and I want to measure the peak area over this time area if I'm doing it in two different places. And it's going to give me a very small number, right? And that very small number is going to reflect what that noise is over that period. And so if you did it a couple of places on the chromatogram, and you have to plan this ahead of time, right? Because you can't go back into the chromatogram easily, right? But you plan this in. Then you can say, all right, my peak area, which has the units of microsiemens dash minutes, right? My peak area over here is going to be some number. My peak area over here is going to be some number. And I can then use that, maybe they're very similar, probably, and I might be able to do that over 1 or 2 different chromatograms. And from that, I can just take that peak area and multiply it times 3 to estimate a detection limit based on this approach. So you need to do this, or inject some blank 3 times. And if you inject it 3 times, look over that same area where your peak would normally be eluting, and see what that peak area is, right? That's the alternative that it takes.
First, what you're describing, are you just like picking random spots to integrate that would seem to be just flat?
Yes.
See any of it doesn't matter.
Yes. Where there's no peak. Right. So you need to pick an area that is what you consider your confidence the baseline, not for something maybe they just can't see it. You might want to go into that chromatogram and expand the axis, the y-axis, substantially to make sure there's nothing there, no surprises, right? It's just baseline noise, and then you integrate with that area that's of a similar duration that your peaks can move.
You have to integrate over the same like width for each of them.
Well, if you were say optimally, you'd say I can do 1 blank, and then I go and do 1 blank. I could shoot 1 blank, and then I would look at this, and I'd look at this, and then you do that. That's the other approach, right? If you had 1 blank, if you had no blanks, then you would look here and look here in the baseline. If you shoot 1 blank, you could look exactly using the same set of chromatogram analysis setup and look at the peak areas in the same intervals where you normally do your peaks. However you do it, all you're doing is you're estimating what the baseline is and then multiply that times 3. And the way you do it, you should just be able to describe. They're all acceptable. You just need to be able to describe this way.
Earlier you said, yeah, you find multiple of them.
well, these should, if you did it, if you were trying to derive the baseline noise from a chromatogram where you actually had, checked a sample or something, then you would be looking between peaks where you are certain that there are no analytes eluting, so you'd expand that axis. And you could look at multiple places in that chromatogram where there's no peaks eluting. And in principle, the baseline noise should be the same or very similar across those three, right? And so you could say, I'm going to look at these and maybe average those two, and I'm going to apply it to the entire run. There should be, the baseline noise, in principle, should not really change over the course of evolution, because it's coming from the detector.
So when you find that number, you multiply by 3.
Okay. And then what do you do with it? So now, if we did this, now I have some number, because of how I integrate that, where I have its peak area. So now I have my peak area of my baseline, right? I then multiply that times 3. So this is my noise, right? I multiply that times 3, and now I get a bigger peak area, right, in my baseline, right? Now what do I do with that?
Subtract it?
No, divided by your slope, when you standard curve, right? For each analyte. Because the detection, what units of detection are they in? They're not in peak area, that means nothing, right? They're in milligrams per liter, or whatever the units are for their analyte, right? So you would take this peak area, just like you did for experiment lab 1, and you would convert this from the units of your detector response. In this case, it's going to, microsiemens per minutes, and into a concentration, because that's what matters to us. Right? And to do that, you would just simply take that number, okay? So now it's 3 pK, let's say, and you then divide by the slope. Okay. And the slope has the units of what?
Microsiemen per ppm, or like microsiemen per concentration.
Right. In your case, it's going to be microsiemen minutes, right? Because you're doing area per concentration, per milligrams per liter, or whatever, right?
Yeah.
And so the units of microsiemen minutes will cancel out when you divide by slope. You'll be left with concentration, right? That makes sense? It's important that some people didn't quite get this, but it's the exact same process, but you obviously need to come, in this case, to concentration in milligrams per liter for your detection of it.
So this LOD for the chromatogram is the single noise ratio, or so we're gonna have a separate one that's like our limit of detection on the standard curve that is like our, or is they're gonna be related? They're gonna be the same.
Well,
Like, because in the last lab report we did 3 times standard deviation plus the blank. So we be using that method for our standard curve.
okay, so I'll answer that. So when you do this, you'd say, I'm getting all my analytes here, and but my baseline noise should be the same whether it's here, here, here. If I shoot a blank, then I can get this for each of my analytes. It should be almost the same, but I can get it for each of my analytes using that software, the parameters I set for which areas to integrate for along the evolution, right? That makes sense? Yeah. So I get those different microsiemen peak areas per minute, peak areas for each of those along the baselines. Then I'm going to divide those by a slope that's different for each peak, for each analyte, right? Because I'm getting one slope for my chloride, I'm getting one slope for my sulfate, one slope for nitrate, or whatever. So they all have different slopes from my standard curves, because in your report, you're going to have one graph for each analyte for your standard curve, right? And you'll get one slope for each analyte. And then you'll divide that number by the slope for each of those analytes. And so you'll get a detection limit that'll vary for each analyte depending on what the slope was for that analyte. Is that what you were asking?
Kind of, well, I mean, I can understand if we did this, if our line went through zero, because then we'd only have our slope times x equals y.
Yeah.
But so, would we, if we have a y-intercept, also incorporate
No,
that?
I wouldn't, I don't think that's, no. So you just divide by the slope, you would not incorporate your y-intercept.
Does that mean that on our standard curves, we're gonna force it through zero in this
No.
case? But
No.
we just don't use it. We keep the same slope.
In this, you just don't use it.
Okay.
You would use that intercept and calculate the concentration of your unknowns,
Mhm.
right? But you don't, you would not, do not use it in doing the detection. Just use the slope. Okay. Okay. Does that seem clear enough? If it's not, we can talk a little more after class about it. All right, so I'll just quickly say, when we look at fixed variable wavelength kinds of detectors in liquid chromatography, you know, this is like what you've done, what you've seen, you can already see this, but you had a D2 lamp that was generating this polychromatic light that was then going through a monochromator and a slit and selecting a particular wavelength, right? We've talked about that a lot. In the simpler fixed wavelength detectors for liquid chromatography, rather than a deuterium arc lamp that generates this polychromatic light that's then selected, they oftentimes will use a mercury lamp, and they have mercury vapor inside that lamp that when it's ionized, it generates an intense line at about 254 nanometers, and so that's the only wavelength of light that it's capable of emitting. So this is only good for measuring things in biological samples because aromatic rings on amino acid side chains absorb pretty strongly at 254 nanometers. So that's how they achieve that. The diode array that I mentioned, you still start with something like a D2 lamp, and this shows sort of diode array in UV vis spectrometry kind of setting, as opposed to liquid chromatography, because they have a cell here. The same process, if you had a flow-through cell where your sample was coming from your column, is the light comes through there, and you have the different wavelengths of light that get that strike a gradient, like a monochromator gradient, like we talked about, that separates the different component the light into the different component wavelengths. And they're all simultaneously detected on a photodiode array. And so rather than measure one wavelength at a time that you select, like you did in UV-Vis, you can measure many, many wavelengths all at the same time. And you'll see when we go on and talk about atomic absorption and atomic emission profiles, most of the instruments now are fitted with a CCD detector, just like exists on the camera, except much higher quality. And those CCD detectors can detect at the same kind of thing, many different wavelengths of light simultaneously. That's a huge advantage. Okay, I'm going to leave this here. I'm going to move past that and start a little bit of what I wanted to start. Let's see. And I want to switch gears now a little bit and talk about, start introducing atomic absorbance. Are there any questions on chromatography and stuff? How's that? After class. Okay, so we are now rapidly moving I'll swing by lab today, so that's what we talked about, and tomorrow it wasn't clear, we clarified in lab today. Okay, so we're moving from looking at methods that allow us to detect, separate, detect, and measure molecular species in a sample. We started with utilizing ligand complexation of copper, and we were measuring the molecular complex of the copper ligand complex, the UV-Vis spectrometry. And with the liquid chromatography, we're separating not just some atomic anions, but also some molecular anions. But typically in chromatography, they're measuring species that are molecular molecules, not just one atom. And
so we're moving from that now to start talking about measurement methods that are based on measuring things at the atomic level. And so molecular absorption spectroscopy relies upon a very different set of principles, some very similar but some different, than does atomic absorption spectroscopy. And I want to start this because it has so many applications in a lot of these atomic spectroscopy measurement methods, so many applications in the real world that I think are very important. And so I start this because we've done a lot of research looking at environmental lead levels over many, many years. And lead, you're all familiar with, is element in the periodic table that you may not know has absolutely no biological function, but has a huge array of different industrial applications. And we used to put lead in gasoline long before you were born, but not when I was born, and not before I was born. And we used to put lead in gas to the quantity of about 2 grams of lead, which is about enough to fill the palm of my hand, per gallon of gasoline. So for every gallon of gas we combusted, 2 grams of lead was aerosolized in the atmosphere and fell out. And we did that for 60 years or so. And so there's nowhere you can go on the planet and find natural levels of lead in any kind of environmental measurements anymore. We've been so successful in that contamination. And so the EPA, the Environmental Protection Agency, actually is the agency that's responsible for helping to regulate the discharge of things into our environment by different industrial manufacturing processes and so on. And they set an air lead standard back in 1978. That's when I was, younger. 1.5 micrograms of lead per cubic meter of air. And that standard stood until 2008. Let's see, somewhere maybe, until 2008. So it stood for, 20 or 30 years. That standard stood before they finally revised it and lowered it to a new level of 0.15 micrograms per cubic meter. So they went from 1.5 down to 0.5, a 10-fold reduction. And of course, the reason they do that is because to help protect the health of us, right? Because lead is very toxic, there's no biological function, and for many people, the way we get exposed is through the air we breathe. Right? So there's a very interesting and important analytical component to this story. It starts back with this guy. And so this guy, his name is Claire Patterson. He was a professor at Caltech. He's dead now. But he was a guy that started getting into science, got his PhD at the University of Chicago back in the days when all the nuclear physicists were going to school in Chicago to other universities right before the war, World War II. And they were the people that were recruited to develop some of the theoretical constructs that led to the development of atomic weapons, all these things, atomic age, right? He was part of that, and he was a geochemist, an isotope geochemist, and he graduated and went to work at Caltech, and his whole thing was using lead isotopes, because lead exists in different stable, not radioactive, but stable isotopes. And they developed a method to look at the stable isotopes of lead in different rocks, because he's a geochemist, on Earth, and compare that to the stable isotopes of lead that were in meteors that were hitting the Earth. And they were able to use, knowing how the lead isotopes are decay products of other radioactive elements like uranium and thorium, and how long it takes them to decay, they were actually able to look at those ratios and estimate how old the Earth was. And he was among a group of people who first estimated the Earth was 4.5 billion or whatever it was years old, using these lead isotope measurements in meteors and Earth rocks and stuff. So it was a big deal. Of course, they revised that. Now they've got a little bit. Now people really, it's really cool because they can get it down to 3 or 4 significant figures. But the people that first did it were people that were looking at these lead isotopes. He was one of them. After he did that, he then got interested in understanding, recognizing that lead is a problem. Lead's toxic. We use a lot of lead. At that time, when I was like your age, we used lead in gas. We use lead in solders for sealing cans. We use lead in paint. We use lead in all these things, right? Even though we knew lead was pretty toxic. And so he got interested in trying to
demonstrate and document sort of how the evolution of us producing lead and discharging lead in the environment has changed over the course of history. And he generated this plot. And what this plot shows, these are thousands of years before present, so we're here, right? And this is a log scale of estimated tons of lead produced in the world. And about half of all this lead on a yearly basis is produced, ends up in the environment as waste. And so he said, well, at some point when pre-industrial, prehistoric humans discovered the process of cupellation, which is the process of taking precious minerals out of the ground, like gold and silver, and smelting those minerals, smelting those rocks to extract the precious minerals, and leave behind what you don't want. Once they discovered that process, that's what, of course, led to the Bronze Age and all these things of using smelting metals to make spears and weapons and stuff. And huge advance in human civilization and evolution. Well, when they discovered that, then the production of lead started to increase exponentially because lead, like all these other elements, they coexist in these rocks, these ores. And so whenever there's gold and silver and all these other precious metals, there's always a lot of lead. In fact, usually more lead than most precious metals. And so when you smelt that, what you have is precious metals you isolate this much, and you have tons of waste lead.